Hello, my name is Daniel. I work at Wolfram for IBD, International Business Development. I work and live here in Brazil, attending clients in the region. And at the same time, I give classes in college after hours for post-graduation in data science. Today, I'm going to talk about two functions I have published in Wolfram Function repository. Recurrency plot and cross recurrency plot. Basically, those are visualizations for time series, for data science, complex systems and statistics, very useful, very well known, and I did the implementation in Wolfram language. To see a definition, okay, I have my own definition. In short words, it's a visualize patterns in numerical and sequential vectors in lists. We have a 2D graphic, that's a binary graphic that shows by the time when the values from two different lists, from two different numerical vectors, they are closer one another. Here, for example, the first case we have here two random lists, integer lists from 0 to 9, with 30 elements in the list, 30 numbers in the lists. Those, of course, they are different lists, and then different random lists. And then in this graphic, it's in this binary matrix, the black dots, the black squares means that the values from both lists, they are closer one another. This is a definition I like. This definition is in the recurrence plot website. That's a very nice site to learn about. They have even a conference about recurrence plots. It's really interesting. As this is in fashion, I synthesize here a description about what a recurrence plot is using GPT-4. I highlighted this here in orange. This is a description from OpenAI, GPT-4. And then I did another one. I get together the information from Math World. There is a web page describing recurrence plot. And there is a Wikipedia page about the recurrence plot too. I joined them here as a string, and I use this text to summarize function in order to have another vision about what is recurrence plots. But in this presentation, I'm going to show you a lot of cases and a lot of examples to clarify and show how I did the implementation for the function. First of all, how to read a recurrence plot. Usually a recurrence plot is a binary matrix, okay? We have black and white dots. And when we can notice the pattern, and the pattern means the kind of information we have in those vectors as input. The first one, they say that the type A is a kind of random pattern. The second one is repetitive pattern, that is a periodic pattern. And the C and D is almost a combination. We can see they have some randomness and some repetitive patterns at the same time. We have here, for example, the diagonal. We may notice that the diagonal, they coincide, and they show that the data at both vectors in both axes, they are the same. And so we can see this diagonal line where we can notice that both vectors, they are equal. Here's the definition from the recurrence plot website. So they say that this A is homogeneous, the B is periodic, this C pattern here is a drift, and this other one is distributed. It's a kind of random distribution. The randomness is distribution in some clusters, in some region of the visualization. It helps us to figure out what's going on with the data. The data is ever a kind of signal, numerical, can be float or integer values, and then we can see how those signals evolve on time. I have links for reference for all the, basically all the slides here. The first example, the first case here, I can compare trigonometrical functions. It's very popular when you see in books and articles discussions about the usage of recurrence plots. They show it in trigonometrical functions because it's easy to understand. Here in my manipulate, I have here a table, a discrete, I'm generating here a discrete signal, one for sine and the other one for cosine. And then I load this in those variables, and then we load and visualize the recurrency, in this case, the cross recurrency plot. The cross recurrency plot, I am using two different signals, the sine and cosine by the x, one by the x-axis and the other one by the y-axis. And so we have this thing here. This is the yellow one, a yellow and orange is the recurrency plot graphic. And here at the top, we have the sine and the cosine functions, okay? The discrete versions of them. And then I can vary here the frequency of those functions, and I can notice the change in the visualization. I can change here the size of the sample, and here we can see the patterns, what happens with this recurrency plot. Here, the case of the cross recurrency plot visualization. This is a binary visualization. And then we can notice related to the sign or to the how the sine and cosine, they vary by time. And this representation here in the binary form. I have another example here comparing to simple lists. For example, this one, I am using the recurrency plot, and then I am creating here a random value again, a random list, and then I have 30 numbers in the list, varying from 0 to 9. And then as I have just one signal, just one vector here, numerical vector, I'm sending this as parameter to the resource function recurrence plot, and then I can see here the same vector is in use and at the x-axis and the y-axis here at the visualization. And again, when we see those black squares here, it means that the values from the list, the numerical vector, they are very close one another. And of course, here in the diagonal, they all coincide because they are equal in the diagonal, because we are comparing the same signal in the y and x axis. Here, for a more simple example, I'm showing the list here. We input by hand, and then we can notice, for example, here at the middle, we coincide exactly the same values. Here, the values are close, okay? And then we have we can see here that they coincide. when they are in the black dots here. And then when they are different, when they are very different, they are in whites and black dots here. This is a recurrence plot comparing two different signals, two different vectors. Here we can control, there's a threshold to decide where the values should be black or white. And then we can control this threshold, and we can notice some difference here when we change this threshold value. Here it goes from .1 to 2, and as they are changed, we change the kind of tolerance we have in the comparison of the numbers in order to create the visualization. We have another option that is the global cross recurrency plot, or the global recurrency plot, where we one threshold. Okay, we bypass the threshold, and we see all the values that are calculated. And so we see here all the values, doesn't matter if they are higher or not. We see all of them, the higher values and the lower values in the cross recurrency plot. Here I have another case with this on threshold, that is the global recurrency cross recurrency plot. We send this parameter here to bypass the threshold, and then I'm comparing the range to 10. Okay, so those are basically the same values. I'm using the cross recurrency plot, but I'm sending exactly the same values, and so we can notice here they coincide in every case. Here they coincide, and then I can, for example, to do the same thing with the recurrence plot. Here I am using the cross recurrence plot resource function, sending the same signal twice, okay, with the same value. And here, using recurrency plot, when I send just one signal, because this one signal is used for both the x-axis and the y-axis. In fact, we may see that the graphic is exactly equal for the global currency type. Another thing we can do to highlight the visualization is to add the color function here. In fact, this recurrency plot and cross recurrency plot functions, they support all the parameters from array plot. Okay, they are based on the array plot function, and then we can send any parameter from array plot here that it's gonna work. Here again, we have the cross recurrency plot visualization to compare two random vectors. And here I have a random integer from 0 to 10, and here I get 0 to 10. Of course, they are different. Those create two different random lists with 100 elements in the list. And then using cross recurrency plots to compare those two guys here. And then I'm setting those parameters here. They are from the array plot, standard from the array plot. And so color rules and frame known. And then I can see here how the pattern behave. And those orange dots here, they means where the two random signals, they are very close in still a binary matrix. Another example here, a trigonometric function again. Here, what I do in my manipulate. I have two equal functions here, sine and cosine, but I will vary here by the sliders the frequency of those functions, okay? And then I'm using the recurrence plot, getting this discrete list from a two trigonometrical functions, and then we can compare. We can change the frequency of both of them and compare to see the visualization here. Here we have both of the signals here. Here we can vary the frequency. And then here the size. You can change the size of the sample we have. And here we have the recurrence plot, where the dark dots here, they are the place where the signals, they coincide. They are closer to one another. Here we can compare what we see in the signal by the time, and here how they behave, what's the pattern in the cross recurrency plot. Another example here. This is from computer science. I have an example from elementary cellular automata. I have here a manipulate. I'm using the same random list as input for both cellular automata rules. We have we plot the rule, and then we use cellular automata to develop the pattern, and then we can compare both of them. I count here. We transpose the cellular automata and run the total. And so what we do here is counting the number of black dots for each cellular automata rule, and then we send this information to the resource function cross recurrence plot, and then we can compare both numerical vectors. That is the sum of each step of the cellular automata. And then we have here some controls, and here we can change the rule. This is the first one, and this is the second one. And then I can change them. For example, here we have the rule 43. Here is the 157. And then here we have this graphic here. It shows the counting of black cells at each line, at each step of the cellular automata. And with this information, we use this information here to create a cross recurrence plot in the global version. So we are not using the threshold. We are showing all the intermediate values that compare both signals. And here again, we can change the cellular automata rule here and compare in a global cross recurrency plot how they behave, looking at the pattern. I can change the size here too, and then we can see how they behave. For example, I can try to compare here. I can try to compare rule 110 with the rule 30, for example. Rule 30 is known as to be the one that creates random numbers, and then the rule 110 is the one that does universal computation. Here we have both. We can compare rule 30 with 110 in the global cross recurrence plot, and we check when they coincide. This is the fifth case about data science. Here we have the Wolfram data repository, this classic from data science education that it is botanic research data. And then I import this data here. It is here in a data set. And then to send this to a recurrency plot or a cross recurrency plot, I need to change the categorical data. And so the text columns here, I need to change that to a numerical form, okay? And then what I do here, I create those categories, I convert them to numerical forms here. This is a association. And then I can use this association to do this work, to get a text column, a categorical column, and change it to a numerical version. And here we do it to create a new column here related to this first one that are the species of the flowers. And then we have now species numerical. That is exactly the same data, but here with the numerical representation. And then here I do some cleaning. In fact, I get the data set, just the values, keep out the quantity, and so they have here centimeters, and so I get this thing out, get a normal list, and remove the first column, this first categorical column. And then what we have here is this list now. This simple list is a matrix list of lists, and then we have just numerical values. We have floats and integers. And so we can send this data to the recurrence plot, and then here we can clearly see the clusters of the three species that are in this data set, in this research data set. We clearly see the pattern here, the dots, the black dots, they are the points where the values, they are closer to one another. And then we clearly see the clusters here from both three different species from the IRIS data set. And now the same, we are using here the same data, exactly the same data, exactly the same recurrence plot, but with the global type of recurrence. And so in here, in this case, they are unthreshold. They ignore the threshold and they show all the intermediate values for us. And then again, we can see the clusters, the three clusters here that represents the three species of flowers, but we see all the other occurrences here, all the occurrences values calculated, no more in a binary version, but in more smooth visualization. And then we have this one, is the last example in financing. Here we are getting data from Wolfram Alpha. We are getting the euro and dollar values for 2033. It's very convenient to use Wolfram Alpha to get real-world data. And they come here in a computable form, so I can just use it. And then it returns a time series, okay? With of course, this time series have 255 samples of data for all the 2023 values, daily rates. If we get one, to spy just one of them, we have this one, the first information. And so, as I did before, I clean up, I remove the quantity from the values and get just the pure numbers here, the float values that represent the ratio of euro and dollar. And of course, we have 255 samples in this list. And I just send the list here to the recurrence plot. And now we can see the pattern. Of course, the diagonal here, they are all coinciding, okay? But we can see by the year when the the values coincide, they recur during the year in this dot matrix. That's a binary matrix. And then we can, again, using the global version with untrusted, without considering the threshold. So removing the threshold, we can see all the recurrence values, comparing both at the X and Y axis, the same sign, the same values from the dollar. And then we can see again the pattern, the same pattern, but basically here we can see the higher points and the lower points during the year of 2023. And so how I did the implementation here. The equation, we have the equation that represents here this recurrency plot, how to calculate all the dots and all the values. We have here the threshold, and so depending on the threshold, it can be 1 or 0. If we hit the threshold, we highlight, and so the values, they are closer, okay? It's not exactly the same value, but they are closer, and then we paint that cell as 1, otherwise 0. And then it's very straightforward to do it in Wolfram language, because in fact we are all the building blocks. We have all the functions we need to implement the equation, okay, and transform this in a computable function. And then we have used unit step, norm, array, and array plot, as all the properties from array plot can be used in this recurrency plot and recurrency across recurrency plot functions. They are already published. You can use it. I'm going to share this notebook here if you are interested in it. And then the next steps for those functions, I will improve to receive the data set as a parameter for recurrency plot and cross recurrency plot. This is useful, is interesting for data science projects. To receive the data type time series is interesting too, and then to receive an association. So the next step is to make those both functions to accept data set, time series, and association data structures as input. Another thing that can be made is to convert categorical data, so text data, to numerical data in order to be used in that calculation in the equation. And then another thing we can do is some automatic data cleanup. I think those two features here we can do using the resources from data set. When the data is sent as a data set, using the data set sent as input, we can do both things here, to convert categorical data, text data to numerical data, and then to clean up, to do an automated cleanup in the data instead of the user do it upfront in order to send a clear list, a clear vector to recurrency plot. Here we have the reference that both functions are published, and then the recurrency plot website is good about, there are lots of information and conferences about that. We have Wikipedia, and then Math World has a good explanation to explore more about what we can do and how to analyze the patterns with recurrency plots. This is my talk for today. Thank you for attending this talk. I will share my this notebook, and this is it. Do we have questions? Okay, we have a lot of questions, but we have already done. We don't have time. I will I will read and answer those questions here offline, because we are in the end of our time. But I thank you very much for your comments here. I can send you back a response, and I will share the notebook. I will share the notebook with you in the website soon. It should be there available for everybody. Thank you very much.